Good afternoon, pre-calculus students. So welcome to my channel again. This is Mr. Chen. So today I would like to talk about that 3.5. So the word problem with the exponential growth model. Along with that, the logistic growth. Okay, so we'll talk about this one first. The bacteria growth. So in general, so we do have the model for the population growth, which is considered y of t. So that equals y0 times e to the power of kt. So y0 will be considered the final amount. And then y0, then that'll be the initial amount. And then k, that's just a constant. And t, obviously, is the time. And e, we already know that it's an irrational constant. So now let me take this one to the new page. So this one, what we got here, it's a bacteria colony, contains 20 bacteria up to 2 days, and 80 bacteria after 6 days. And show the work algebraically. So find an exponential equation that models the given situation, clearly state initial amounts of bacteria. And then for B, when would the number of bacteria be 5,120? Okay, so let me just put it right here. Okay, so let's start it with the annotation. So 20 bacteria, so that means that will be the final amount after 2 days. And 2 days, that's the time, t. And then 80 bacteria, then that will be the final amount after 6 days. And then it takes, 6 days? So for this one, we need to set up two equations. So start it off with 20. So that equals y0, because we don't know the initial amount yet. So e to the power of kt, so 2 times k. So that's the first equation. So the second equation, then that'll be similar. So 80 y0 times e to the power of 6k. So now what you need to do here, you can divide it. So 80 divided by 20. So the second equation divided by the first one, which is, you'll get 4. So y0 divided by y0, that cancel. And then e to the power of 6k divided by e to the power of 2k. So then that'll be e to the power of 4k. And then solve for k. So take the natural log on both sides. So natural log of 4 equals 4k. So that means k equals natural log of 4 divided by 4. So this one, we just want to find out the constant first. And again, initials, we don't know what that is. So find exponential equation that models the given situation. So since we already found out k, so we can plug in a number to find out the initial amounts. So plug in a number back to either one of the equations to find out y0. So 20, so that equals y0. And then e to the power of 2 times natural log of 4 over 4. Again, the value of k, the one that we just found, just plugging back to one of the equation and then solve for y0. So this one is simplified at y0 times e to the power of natural log of 4 over 2. So that equals 20. So one thing that we can do, this one is consider y0, e to the power of 1/2 times natural log of 4. So using that, the properties of logarithm, so coefficient to power. So this one can be written as y0, e to the power of natural log of 4 to the power of 1/2. So basically, once you take that e to the power of natural log, that cancels because that's 1. So 4 to the power of 1/2, it's just square root of 4, which is 2. So it's 2y0. So that means for the initial amount, the initial bacteria, then that would be considered 10. Okay? So find the equation of the model. So we just did it. So A equals, rewrite it. So y of t. So that equals the initial. 10 times e to the power of k, which is k. So that would be what? Natural log of 4 over 2. Okay, so natural log of 4 over 2. And then times t. And for those you might be wondering, this one, can I rewrite it with the simplest form, like 10 to the power of e to the power of natural log of square root of 4 times t? Well, certainly you can do it like that, but this one turns out to be the power of another power, because that multiplying the exponent, it's a power to another power. So that turns out to be 2 to the power of t. So 10 times 2 to the power of t. So that would be y of t. So that turns out to be the exponential growth model. And then when would the number of bacteria be 5,120? So plug in a number right here. And then basically just solve for t. So divided by 10 both sides, so we got 512. So that equals 2 to the power of t. So 512. So that one looks like it's going to be, well, let's see. Would that be 2 to the power of 8? Okay. So try to do that on the calculator. So 2 to the power of 8. Okay, let's check that. Because 2 to the power of 5, then that'd be 32. So 32. And then 2 to the power of 4. Then that'd be what, 16? Okay, let's see what that is. 2 to the power of 8, that just gives you 256. So what about 2 to the power of 9? That's exactly 512. So this one's 2 to the power of 9. So that means t equals 9. Okay? So that's just for the first one. So now to look at that, the other one. So after 4 days, the amounts of chemicals was 80% of the original amount. Again, using the same kind of model. So after 4 days, so the time, and then the amounts of chemicals was 80%, so it looks like this one's going to be exponentially decay. And determine the half-life of such chemical. So again, using the same model, so we do have y of t, which is what, 80% of the remaining amounts, of the original amounts. So 80% of y0, so that equals y0 times e to the power of 4k. So solve for k first. So 80%, so 0.8, so that equals e to the power of 4k. So take the natural log both sides, so we do have natural log of 0.8. So that equals 4k. And then for k, what is that equal to? So it's natural log of 0.8 divided by 4. And then determine the half-life. Half-life, that means you want to find out the time it takes to get down to half-life. So half-life would be what? 50% times y0. And y0 eventually they'll get cancelled. So e to the power of k times t. So natural log of 0.8 over 4 times t. Okay, so now let's take this one to the new page and find out what that is for the time it takes. Okay, snip. So 50%, which is what, 0.5. Okay, so let me take this one over here. Okay, so we got 0.5y, or 1/2 y. 0 equals y0. E to the power of natural log of 0.8 over 4 to the power of t times t. So again, y0 got cancelled, so take the natural log both sides. So this one got cancelled. Natural log of 1/2 is written as natural log of negative natural log of 2, because natural log of 1 minus natural log of 2. So natural log of 1 is 0, so 0 minus natural log of 2, negative natural log of 2. So that equals natural log of 0.8 over 4 times t. And then solve for t. So this one multiplied by 4, so negative 4 natural log of 2. So that equals natural log of 0.8 t. Okay, so this one basically just like natural log, well, coefficient to power. So then that'd be negative natural log of 2 to the power of 4. So negative natural log of 16. So that equals natural log of 0.8 t. So that means the time it takes would be natural log of 0.8 divided by negative natural log of 16. And you might be wondering, looks like it's going to be a negative number, but keep that in mind. Natural log of 0.8, that's going to be a negative number. So negative divided by a negative number, it's going to be positive. So try to put it into the calculator and see what that is. So natural log of 0.8 divided by negative negative natural log of 16. So the one that I found, so it takes about 0.08. Okay, 0.08 in order to get down to half-life. Okay, so this one looks like it doesn't make sense in order to get down to half-life. Okay, so let me just go back to the problem, the original one. So the amounts of chemicals was 80% of the original amounts after 4 days. Okay, so that's what we found. And then determine the half-life of such chemicals. So what I did first, I just solved for K, using that the same equation. So natural log of 0.8 both sides. So that equals 4K. So K equals natural log of 0.8 over 4. And that's what I found here. So let's go back to this page. And then in order to find out the time it takes to get down to the half-life, so it's 1/2, 50%. So natural log of 1/2, which is the same as negative natural log of 2. Okay, so take the natural log on both sides here. So this one got cancelled, so natural log of 0.8 over 4. Okay, so divided by 4, that means you multiply by 4 on both sides, so that's what I did. And then I condense it, so it's negative. Okay, you know what? Instead of condensing it, let's just keep it in this way. So just solve for t normally. So t equals natural log. Oh, you know what? I divided the number incorrectly. The other way around. Okay, so once again, I apologize for this one. So instead of dividing by natural log of... Wait a minute. Yeah, instead of dividing by negative natural log of 16, so we're supposed to be dividing this one by natural log of 0.8. Okay, so the other way around. Yeah, that's why we come up with a small number. It's a very small number. It's almost getting close to 0. Okay, so this one, the final form right here. Okay, so you guys just find out right here what I did wrong. So divided by natural log of 0.8. So do that on the calculator. So negative natural log of 16. So negative natural log of 16. Oops, going back to the normal window. Negative natural log of 16 divided by natural log of 0.8. Okay, so eventually. So it takes about 13 days. Okay, because this one you want to round it up. It's about 12.425. You don't want to round it down, then that won't be exact. So it takes about 13 days. Okay, so t equals 13 unit days. Okay, so now back to the template. Okay, so this one is something I want you to think about. So write C in terms of that A and B. So the hint, so you probably want to rewrite it. 4 to the power of A, it's like 2 squared A. Okay. 25B, then that'd be 5 2B, 5 to the power of 2B. And then 100C, then that'd be 10 squared C. And then this one you want to solve for C in terms of A and B without the logarithmic form. Okay, so think about it. And then for number 4, so an African preserve can sustain 2,400 olivins. So 40 olivins are released. And after 4 years, the number had grown to 60 olivins. So find the population up to 10 years. Okay, so this one is called the logistic growth model. So this one, it preserved. Okay, so this one preserved can sustain 2,400 olivins. So this one is called the capacity or the maximum capacity. Okay, so let's say M. and this one obviously the time here. So 40 elephants, so that's what we started first, the initial amounts. And then, so it grows to what, 60 elephants, so then that'd be the final amount. Okay, so normally the logistic growth model can be represented by the equations like P equals capital M over 1 plus A0, which is the initial amount, times e to the power of negative kt. So this number right here, maximum capacity, that means, when t goes to like a big number, to like 1,000 year, 10,000 years later. So it doesn't matter which year that goes to. So the maximum, so the number of elephant, it can be sustained here for the preserve. So that would be considered 2,400. Okay. So in other words, that means eventually, so the horizontal asymptotes, okay, it's going to be considered m, the value of m. It's always the maximum capacity. Okay, so you can sketch the graph for that. But if you try to find m behavior, you'll see that eventually this one's going to be getting close to m. Because when t is getting bigger and bigger, this number is getting smaller and smaller. Okay, so eventually, this one turns out to be 0. So 1 plus 0 is just 1. And then m over 1 eventually is going to be m. So for the asymptotes, the horizontal asymptote, it's going to be considered the maximum capacity. Okay, so now let's find out that the population is up to 10 years. Okay, so there's so many things involved right here. But also we need to find out k. So let's start it off with finding the value of k from the equation. Okay, so a lot of things going on for this one. Okay, so one thing at a time. So let's start finding k. Okay, so what we found here, the maximum capacity, so it's 2,400. Okay. And then 1 plus A0, so started with 40 elephants. E to the power of negative kt, we don't know what k is, so negative k times 4, so it's negative 4k. And then the number of elephant has grown to what, 60? Okay, so solve for k. So this one basically can cross multiply, or you can just like divide a number. 2,400 divided by 60, then that'll be what, 40? So that equals 1 plus 40 e to the power of negative 4k. And then subtract 1 both sides, so we got 39 equals 40 e to the power of negative 4k. Divided by 40. So we got 39 over 40, so that equals e to the power of negative 4k. So take the natural log both sides, so we got natural log of 39 over 40, so that equals negative 4k. So that means k equals negative natural log of 39 over 40 divided by negative 4. So keep this number right here. So this one is going to be positive. It's a very small positive number. Okay, so now what we can do after that, so let's just rewrite the model in terms of the value of k. So that means for the preserve, so this one, that equals m, the maximum capacity, 2,400, over 1 plus A0, 40, e to the power of negative, so that turns out to be positive. So positive natural log of 39 over 40 over 4 times t. Okay, so this one is just the denominator extended. Okay, so now find the population up to 10 years. So just plug in the time up to 10 years. So P of 10. So 2,400 over 1 plus 40 e to the power of this weird number, natural log of 39 over 40 times 10. Okay, so try to find out what that is on a calculator. Okay, so on the calculator you can just set up the model. Okay, so what we found here, well, the value of k, it's a kind of weird number, so what you can do, you can always start it with the calculator like this. So natural log of 39 over 40 divided by negative 4. Okay, so divided by negative 4. So you want to keep using this number, so it's an irrational number. So what you want to do, you want to store that number. So go to STO and then alpha A. So we just want to keep the whole number in that letter right there, A. And now we just want to put in the model. So y equals, okay, we don't need that y2. Okay, so y1, then that'll be 2,400 divided by, just want to enter the function, so over 1 plus e, so second base e, to the power of, okay, so going back to this page, so to the power of, well, this one's supposed to be negative number, so I still need to put in that negative, so it's going to be negative a times t. Okay, so here's what you want to put in. So negative alpha, because we just stored that number in A, alpha A. Okay, I put in 2, so we don't need that negative 2 there. Delete. So negative A times the variable t. But in this variable here, so this one is just x. And then bring down the cursor, close parentheses. Okay, so that's the model we want. And now we want to find out the populations after the number of elephant after 10 years. So go to second graph and then type in 10. So you see that it's what? It's about 1,238. 1,238. Okay. So 1,238 elephants. And then when would the population reach 2,000 elephant? Okay, so 2,000 elephant. So this one, try to do it on a calculator. So 2,000. So that equals 2,400 over the same quantity. So this one is a calculator problem, so we want to put into the calculator, so e to the power of natural log of 39 over 40 times t. So the way to do it, so going back to y equal, so for the next one here, so we just want to put in y2, so y2 with 2,000. Okay, so this time we want to find out the value of x. So when that's going to be reaching to 2,000. I mean, you can use the xy table, but the best way to do it, so you probably want to find out the point where they intersect. Okay, so this one, go to zoom or go to window first. So change the scale, so x min, change that to 0 because we started with 0 year. So 10, that's kind of small, we just find out that the number. So let's say that, make it bigger. Probably 40. And then the y min scale, so started at 0. And the y max, we do know the capacity. The maximum capacity is 2,400, so let's make it 2,500. Just want to get some space to see that, the whole graph. And then everything else, just keep the same thing. And then hit graph. So check it out, the constant line right here. So this one, it just shows that it's the, which is what, 2,000. So as you can see that this one is just like, keep going. Okay, kind of like a straight line here, but it's supposed to be like a logistic growth. So it's like an increasing curve, and then it just slows down. Okay, so what we can do here, we can just change the window. So besides 0 to 40, so let's change that to 0 to 100. Okay, and see what happens. Okay, so it's getting close, okay, eventually. So let's keep going. Window, so let's say 300 maybe. Okay, eventually they're going to intersect. Okay. So let's find out the point where they intersect here. So second trace. and then intersect 5. So now the calculator is asking about the first curve. It's always starting with the first functions, the blue curve. Enter. Second curve, the line, so pass through the point where they intersect. Enter, and then press enter again. Here we go. So in order to get that the same population, 2,000 elephants, so it's going to be taking that, it's about 254 years. So 254 years. And then for C, graph the functions represent the logistic growth of the elephant population. Explain the meaning of the asymptote. Describe the graph in terms of the growth rate. Okay. So this one, let's just make a bigger scale so you'll see what happened here. So going back to the calculator mode. So y2, we don't need that, just the original function. Clear that, y2. And then back to the window. So what I did here, I started with 0 and then 300 and then the scale 1, 0. Y max, I used 2,500, okay? And everything else, just keep the same thing. So again, hit the graph again. So basically this one, it just shows that the logistic growth. So as you can see that the graph is increasing, but somehow, once that the time is getting bigger and bigger, so the number of elephant eventually is going to slow growing. It's going to be slowly growth. Okay, so that means this one right here, it slowed things down here. It's going to be what? 2,400. So there's like horizontal asymptotes right here. So that means as t getting bigger and bigger, so y, it's getting closer and closer to 2,400. Okay, so what that mean here? So that one is just the HA. So y equals 2,400. The maximum capacity. And describe the graph in terms of the growth rate. Okay, so that's what I just mentioned about. So we started with like a dramatic growth, but somehow, time is getting bigger and bigger. The rate of change just slows down. Okay, so we can describe that. And explain the meaning of the asymptote. That's what I just said, so because that is just reaching to the maximum capacity. So eventually it's getting close to 2,400 in order to sustain 2,400 elephants. Okay, so now let's see what else that we have for the rest of the lesson template. Okay, back to this page. Okay, so the other one, it's about the earthquake problem. Okay, so this one, how many times stronger to the nearest integer is that 9.2 earthquake than a 7.9 earthquake on the Richter scale? So normally the magnitude model is like log of I over S. So what that means, M is the magnitude, so I is the intensity of the earthquake, okay, and then S would be the standard scale. So in order to find out the comparison, we don't just divide it, okay, so make sure that you don't just divide those numbers. So what we got here, 7.9. So this one would be considered log of I over S. Okay? But in order to compare those two magnitude, so let's say this one is the magnitude of that 7.9 earthquake. Okay? You know what? M would be the larger one, would be the larger number. So that would be 9.2. And then there's a time right here. So let's say that one is t or x. Okay, that's what we need to find out. So basically, in order to compare that, it's m equals log of the quantity I over s times t. Okay, so the whole quantity. So basically that it's 9.2. So that equals log of t I over s. So what we can do here, we can use the properties of logarithm, expand. So 9.2 equals log of t plus log of I over s. Again, log of I over s, which is what, 7.9. So plugging the number, so we got 9.2. So that equals log of t, so plus 7.9. In order to solve for the time, the number of time, So what we can do, subtract. So 9.2 minus 7.9. So we got 1.3. So that equals log of t. And then solve for t. So basically convert it back to the exponential model. So 10 to the power of 1.3. So that equals t. And then just find out what that is on the calculator. So 10 to the power of 1.3. Let's see what that is on the TI. Okay, so 10 to the power of 1.3. So it's about 20 times. If we just round it up to a whole number. 20 times bigger. Okay. Again, the comparison, we don't just divide it. Okay, so we've got to be very careful. We don't just divide it by, the magnitude. So basically this one, we have to do the comparison. So n, the higher magnitude compared to the original one, with the t right in between that law and I over s. Okay? So it's about 20 times bigger. Okay, so any question that you have, make sure that just rewind and fast forward to the part of the word problem that we're talking about. And also, make sure that you watch the other part of the video. Alright? So I'll see you guys next time.